to be zero, all of it has to be renewable, right? You know of a single, I know there's grid independent houses in New York. My uncle used to build them here in the 70s. Yeah, you know, with the rock bins underneath and the big fans, and things like that, and the mold growing under there. Are those zero energy buildings, even if they have enough PV? What almost always happens?
They use fuel.
They use for what?
Heating.
Well, sometimes they have supplemental heating. Cooking is the killer, right? And so what do they do for cooking? Propane. Where did the propane come from? The propane truck.
The PV's not powerful enough to support an electric stove.
Usually not. And even if it is, does it ever get cloudy here in New York?
Occasionally.
Occasionally. So the general rule is usually what? You design the PV kind of for grid independent for like 80% of it, and then you say, you know, after that I need 10 times more PV to make up that last 20%, and so I just go get myself a little generator, right? Zero, no, not according to the definitions.
What if you fueled it with biofuel?
Well, you can get pretty exotics. Now you need a biofuel generator, right? There are definitely ways of doing it, right? But in general, you know, a lot of the grid independent houses are not zero. And so we do tend to rely on the grid. We'll talk a little bit more about the hierarchy. Prioritize within the footprint and then on site, right, first. It's always best to use the footprint of the building. Have that as close as possible. Conceptually, it's a building with no adverse impact. We could spend a long time trying to define what that means. It's not that easy to define. I sit on a task force with the International Energy Agency, and the Europeans, they say, well, on our zero energy building definition, according to the EU directive, we ignore plug loads. Serious! Serious! Right? I don't know. Might not be able to distribute the tape, right? Right? A couple of problems with that is, are you going to put a separate meter in everybody's house just to measure plug loads to see if the building complies? And the second problem is, well, what about the plug loads? It's the big growing hidden sector problem, right? We'll talk about that this afternoon, how NREL tackled some of that. Oh, some other good ones. Does everybody know what a zero electricity building is? I read about a warehouse in New Jersey. Where are our marketing people? Right? New Jersey's first zero electricity building. Right? What did they do? It was a warehouse. They put in a big old gas turbine. Started exporting electricity. Right? Pretty clever, huh? Right? It's like, well, it sounds like a power plant. Isn't that what a power plant does? Right? So these terms start coming up. Zero electricity building. Oh, another one I've heard. Near zero. I just built a near zero energy building. Everybody know what that is? That kind of goes right there with green and sustainable and all that stuff. Yes?
On the topic of boundaries, the grid itself, its ability to do net banking becomes a real problem as the percentage increases. And so I guess the question is, as you go about designing like a nice, omnipotent definition of zero energy, do you want to sort of try to, are you concerned about minimizing the need for grid banking with your surplus as an important, parameter?
Let me talk a bit about that in a minute.
Okay.
And if I forget, remind me. Okay? So really we look about what is the energy transfer, what is the energy performance metric, how are we going to measure this? I can take this building today and make it a zero energy building by cutting the power line. Very easy. So there's also this other piece that's called level of service. What is the expected level of service of the building? And how do we meet that level of service? Okay? It's not practical to disconnect this building. It does happen. Where is the boundary bold? Right? And that's some of those issues. How do we define where that boundary sits? So, yes?
To the level of service, expectations at level of service is part of, do you think there's an important role for architects or whoever designers to try to dampen for energy use? Do you think that our expectations of energy use is just sort of grown too high?
My personal opinion? Yes. The average American citizen, you know, it's a right, isn't it? In some ways. I can use as much energy as I want. I mean, my household, I'm sure, uses less energy than the average American home. Right? My kids are my little energy zealots running around, turning everything off. You know? And that's a culture which my household lives in. And so, you know, there are definitely some behavioral, cultural things to deal with. We'll talk a little bit about this afternoon, the culture issues of us moving into a zero energy building, because we had to take from both sides. It was both the design side as well as the occupant side. Okay. However, we were committed to keeping the building comfortable. Now, whether comfort is defined as you would have thought of it historically, 72 plus or minus 1, that's a different discussion. Okay. What is comfort and what are people used to? Okay. There's also a dialogue that and you know, there's this whole thing about the word conservation. What does conservation sound like? Especially those of you that ran through the 1970s. Got to put on the Jimmy Carter sweater, or whoever came up with that, right? And we got to get the building a little colder, and we're going to have to suffer a little bit to pull through this, right? And the term changed to energy efficiency to try to, you know, say we can do the same amount for less.
Yeah. But that's coming full circle, because it's accounting which gets you to where you go. So you can have an extraordinarily efficient light and 10 times as many of them.
Yes. Oh, yeah.
So efficiency isn't the only answer to the
Yeah.
question. But conservation has got to be part of that design-making process.
Well, it comes down to, is it an appropriate lighting design, right? And there's also bad decisions that were made. I was out at, I think I was out at Seattle Tacoma Airport a number of years ago, went on an energy efficiency tour, and they were very proud in their baggage area. They'd just gotten rid of all of their T12 lamps, right? And they had replaced them with new technology, CFLs, and they had a lot of them, right? And I sat there and started counting. Well, their lighting power density went up from taking out the T12 lamps, because the efficacy of the lamp is actually worse on the CFL. But it was new energy efficient technology. They probably got a rebate for that too. Right? You know, that kind of stuff happens. I mean, there was a grocery store where I used to live in Colorado that took all of their T12 lights out, and they ran all their two lamp T12s and replaced it all with 3 lamp T8s. Energy efficient retrofit. Right? You know, that kind of stuff happens. And I mean, you need sunglasses to go in there. Right? So there's different ways of thinking about what that means. And there's certainly accepted standards of what lighting levels should look like. And so that's part of what we've been trying to work through. Okay, let's go back to this here. Net zero site energy, source energy, emissions, and cost. These are really different ways of looking at the boundaries. We also have a classification system of A through D, and I'm going to have to move right along here. Zero site energy, very easy to look at, measured at the site. Okay? Basically, at the point of the utility interconnect, easy to measure, easy to verify. Now, there gets to be some subtleties here. It can favor electricity over on-site combustion. Okay? You know, think of electric resistance heat. It's 100% efficient at the site. Something else happening somewhere else, as opposed to natural gas, which is, on a good day is in the 90s. But it does encourage energy efficiency designs at the building level. It's not dependent on externalities. It's very easy to understand and communicate. We sometimes get into this discussion about what is the site? How big is my site? But you have to physically draw a boundary at some point in space there. Source energy, a lot of people like to use the source energy boundary. One of the challenges with source energy is, how do you measure source energy? You measure the site energy, and then you apply a multiplier. Where do the multipliers come from?
Portfolio.
Portfolio manager, which gets them from,
Power plants.
okay, power plants, usually, a lot of that has then been analyzed through NREL. And we come up with these yearly average numbers, sometimes by region, right? Sometimes we can use national numbers. Now, what's an issue with that? No fooling. I have had people come to me and say, I'm going to build my building in Seattle. Why is that? Because I will have less environmental impact. I was like, why is that? Oh, because how does Seattle get its power? Hydro. Oh, really? What percentage is the hydro? Is it 100%? No. Where's the rest of it coming from? Call it natural gas, just like most of the rest of the world, right? When I build a new building in Seattle, where do they get the power, the incremental power for that building? Fossil fuels. Because guess what? From the utility's point of view, what is their objective on the hydro dam? They have been maximizing the amount of water going through that dam for decades. That hydro has been fully subscribed for 50 years. Right? And so when you add on to that, you're actually getting, in today's market, probably more natural gas than anything else. But the national numbers do what? They mask all that. Right? So suddenly, Seattle looks good compared to New York. In reality, there's probably not a lot of difference. And so one of the things that we've been talking about is you actually just use natural gas as your multiplier globally. The other thing that happens is those numbers change dramatically with time of day and with season of year. And they're highly dependent on what the utility dispatches. So what has happened to the grid in the last 10 years? Well, not policy-wise, energy mix-wise. A lot more natural gas, right? Cheap, plentiful, cheap to put up the plants, right? And don't we feel good that our greenhouse gas emissions have gone way down, right? Because we're burning a lot more natural gas and we're retiring the coal, right? That doesn't solve the problem on the building side and how people are using the energy. We have to be careful that we don't mask the problem with these site conversion numbers. Did I get through all that? Regional? Not a strong focus on energy efficiency, right? The goal now becomes much more related to how the power is coming to you rather than how you can save it now. Which do you think you have more of an influence on, even if you don't do anything with design? Energy efficiency at the building level, right?
But when you go to source,
Yeah.
it starts to tell you that your electricity isn't 3,412 BTUs per kilowatt hour, right? It tells you it's 10,000
Right.
watt.
Right.
And that drives decisions related to energy efficiency. Says, like, maybe I don't want to use an electric resistance heater because it's not going to just get me 3412, it's going to get me 10,000. Which says now maybe I want to put a deep condensing toilet plant in my building, which is why you use source to drive design decisions.
Well, and I think it's fine to drive those decisions. In fact, one of the things that we recommend is use all the definitions to get to zero. Right? See how many definitions you can. One of the challenges that is out there today is that we are so far away from zero, and any of them are better than where we are today. Right? So be careful not to necessarily use it as an excuse. When we talk about our building later in the day and how we procured it, what we did was we actually we used site because it was easy to understand. But we put a penalty on the energy if they chose to use electric resistance. And we just flat out put a penalty on it. And that helped with that balance piece without mixing, without getting into all this other stuff. Comment?
Just
Question?
a response thought to that, and I'd like to hear you comment on it. Isn't the cost of electricity somewhat balancing the site source issue such that it doesn't really make sense to do electric resistance heating because it's more expensive? So I suppose if anybody's doing a source zero energy building or a site zero energy building, they're going to just put as much money at it as possible. But shouldn't they would also, that would sort of naturally get taken care of by the fact that electric resistance is just more expensive on that.
Yeah, I guess I somehow deleted or still hidden the other two slides on that. Right, so the cost issue, so So yes, so cost
Sort of embodies that source.
it embodies some of that. One of the challenges that we have found is that on a zero energy building, or these buildings that have high PV loads on, or they're not really load, right? High PV inputs, is that it does not change the demand of the building, the monthly demand ratchet. Okay? So when you look at something, and it's caused a real problem out there, because a lot of people have put in all this PV, and where are my economists, how has it been justified economically? They use something called the virtual rate, where they take the annual utility bill and they divide it by the number of kilowatt hours you use, and it's called a virtual rate. It embodies, and that's a very common way to do things like lighting retrofits and motor retrofits and things like that. They do the same thing on the PV. But what happens is that when does a low energy building hit its peak? Okay? Go back to our Walmart store. We did a Walmart store that had 150 kilowatts of PV on the roof. Right? Had another 200 kilowatts of equivalent daylighting inside, 350 kilowatts. The building is chunking along, nice, bright, sunny Colorado day, and a little cloud comes over for 15 minutes. What happens? Lights on, PV off. Same exact demand as every other Walmart store. Okay. Oberlin College has that issue. Right? They export energy from that building every single day, even on the nastiest, cloudiest, foggiest day. At 2 o'clock in the afternoon, that building is exporting electricity, otherwise they'd never make it on an annual basis. And that's a very common thing that we see when we study these. But what happens is they have the exact same demand, kW per square foot, as most commercial buildings. And it does take some management of how to deal with it. And that gets into this discussion about how to deal with it on the grid side. Right? Because when all these buildings are exporting all this nice PV energy at 2 o'clock in the afternoon, who's going to buy it? Right? If everybody's doing it, who's going to buy it? Can't put it anywhere. And so there is this discussion now about how do you store it. Well, one of the problems with storage, I'm getting on a little rabbit trail here, sorry. One of the problems with storage is that storage always comes at an energy loss, right? You got a battery, you put energy into it, you only get 80% of it back out, right? Even the big storage facilities, you guys have, yeah, thank you. Big pump storage facility, what's the round trip efficiency of that? 60, I think it's actually less than 60%. NYSERDA people should know all that, right? Yeah.
So why is it that the buildings that have 75 or all the PV on top have the same load as a normal building? They should be built much more efficiently to use less energy.
So the part that, so the load is less, but the demand is the same. Because at some point, well, other than, yes, so there is efficiency measures like in the size of the heating system, the size of the cooling system, size of the lighting, right? That does come into the demand and that will save demand, right? But the PV sitting on top of it doesn't reduce the demand further. Okay? Because you always end up with this other PV, unless you are very, very clever with the controls. Zion National Park, we were very clever with the controls. Utah Power gave us a rate schedule. We said our objective is to save energy dollars in this building. Because that's what administration, right? Everybody likes zero energy cost, right? Because if I could get a check every month from the utility, that sounds good, right? And so from an owner's point of view, that's very appealing. So most people, most of the engineers say, well, how do I minimize that cost? Because that's going to maximize my value back. We were so good. We had storage in a trom wall. We had storage in even just our hot water. We were able to dynamically change the temperature of different zones based on what the need for the demand was. We were able to keep that building perfectly flat, 24 hours a day. From a utility point of view, what would the utilities say about that? They would love it because if everybody did that, they could have a very efficient grid out there. Right? From the owner's point of view, it was great because we maximized the amount of power and minimized the demand charge we paid. What did Utah Power do? They penalized the building because there was not enough revenue through the meter. Nice. It was in their rate structure. There's a clause that says if you don't pull so much demand spike the demand once a month, once a year, just to get around that. We never actually put that in, but we talked about it in the strategy. So that, again, what was our objective? Remember going back to the test taking, back row here, right? What's the objective, right? We figured out how to maximize what we wanted to maximize for the least amount of cost. And that happens all the time. The other one is emissions. We've talked about emissions, right? What are emissions based on? They're really based on site energy with these multipliers, right? They do start to get into some of this dialogue about, equalness between different sources and how to deal with some of the sources. Right? Some people have said, I don't want to deal with that. Oberlin College made that decision early on. There's a lot of interesting papers and things about their decision to do this. They went to an all-electric building with heat pumps because they didn't want to deal with how do I bring in natural gas and try to export something else. Okay? And that's one way to do it. I don't know if that's totally the most responsible way to do it. Because I think natural gas has a lot of value at the site. It can, especially if you need the heat and can generate electricity with it. So a hierarchy, and I think this gets at some of the dialogue. What we start doing when we talk about zero energy buildings is actually grading, for lack of a better word, what those buildings are. If you can supply all the energy within your footprint, it's an A, okay? And that is the footprint of the building. Because one of the downsides is if I go out in the field out here and put in a PV system, the university decides that real estate is worth more money in a new building for research than a PV panel. What happens to the PV panel? It's out of there, right? And so the footprint is really all you own, all you have control over. We've also put a